Thanks everybody for joining today on this different day than we normally meet. Our speaker is Brad Cowie from the University of Waikato. I hope I said that correct on both counts, Brad. And he's coming to us from New Zealand, so we didn't want him to get up at 4 in the morning to do this on a Saturday. So that's why we're doing this this time, since it's a little bit more convenient for all parties. And Brad is going to be talking today about his work on the Faucet open source SDN controller and some of the experiences that they've had over the past couple of years, and a little bit about the experience that they had at supercomputing 2 years ago. So I will throw it over to you, Brad.
Cool, thank you very much, Jason, and thanks to all the ESNet crew for accommodating me at a different time. It's nice to be able to give this talk at 8 AM rather than when it's still dark outside. And so, yeah, great introduction and pretty good pronunciation. So today we're going to be doing a bit of a deep dive on a sort of deployment. We did a Faucet at SE18, and we're also going to talk a little bit about SDN and why do you want it and that kind of thing. So let's get started. So first I thought I'd start with, you know, why do you want SDN, or why do people like me want SDN? So I've seen, you know, over the last couple of weeks, I've been doing some more traditional sort of networking deployments, and all the vendors have been throwing the SDN word at me, and but they all use it to mean a different thing than what I use it to mean. So I thought I would lay down what my ideals for SDN is. So the whole idea is moving kind of the control plane implementation. So instead of running a distributed control plane provided by your vendor on all the individual routing or switching boxes you have, move that onto general purpose compute, where you've got really cheap CPUs that run really quickly, you've got a lot of memory, you can make a lot of decisions very fast. And also there's kind of the hope that that could be a more open control plane than you have right now, and that could enable you know, more multi-vendor networks where you know, your control plane vendor is different to your data plane vendor. And so the way you achieve that is, you know, forwarding and routing can now be implemented in a language that's much easier to read and modify. So for Faucet, it's Python. Other controllers use different languages. And for us, our routing and switching algorithm, that's all out there on GitHub. You can go read it, you can go look at it, you can go change it, whatever you want. And I think it's kind of neat. And then how do we actually control the hardware? So we're using an open standard to push all the rules down to the data path. For us, it's OpenFlow. There's a couple of different ones that have come and gone, but that's the one we've kind of settled on because it's worked quite well for us. And there's a lot of vendors that support it quite well, which is nice. And there's a lot of benefits to this approach. So we can actually redefine how the network behaves. So that's the D in SDN, software defined. We get this kind of central view of the network for doing all the decision making, monitoring, visibility. There's one point on the network where you apply security policy. So it's quite nice from a consistency standpoint. But there are some inherent problems with SDN. When you buy an SDN switch and plug it into power and plug some ports in, an SDN switch does nothing by default. It drops all packets. Now that's, I mean, a security person's best ideal scenario, a switch that drops all packets, that's so secure. But for people who want to load YouTube or download a science data set, this isn't so great. So we need a controller that starts by scratch, adding the functionality back that we lost by going to an SDN switch. And so we started the sort of Faucet project back 2014, 2015-ish, and there were very limited numbers of controllers. We had a very key simplicity design in mind, but we wanted something flexible, and there was just really nothing that did what we wanted. And Faucet originally was designed for enterprise networks, though as you'll find throughout the rest of the talk, we've found other places you can use it too. So Faucet's, we call it a lightweight SDN controller, just in line with that simplicity idea. It's like 10,000 lines of code, it's in Python, it's very approachable. It also runs on very low hardware resource compute, so you can run it on Raspberry Pi if you want. We never wanted to have the big SDN cluster of controllers. We wanted something much more compact and lightweight. OpenFlow is our SDN API. And going in line with it being an enterprise SDN controller, it does layer 2 and layer 3. It's a, you know, our goal for the project was to do whatever a Cisco Catalyst switch does out of the box. That's what we wanted Faucet to do. We also wanted this kind of policy-driven approach to extending Faucet. So we didn't want network operators to have to write code or modify code if they didn't want to change Faucet's behavior. So it's got a lot of different points where you can put in different policies to sort of augment or change the default behavior of Faucet. And your 30-second sort of crash course in OpenFlow, for those who haven't seen it before, you don't really need to understand it to understand this talk or Faucet, but I'll go over the basics. So you start with this kind of rule-based approach to defining your network policy. So a rule is simply a match, and a match is just matching some number of the headers in a packet, or possibly it doesn't match a header in a packet, or possibly you say, I don't care what the value of the header is, match all values for that value. And then for a given match, you can have an action. And so an action might be output this packet, out this port. It might be drop this packet, we don't want to see it anymore. It might be let's modify some fields in the packet. And then basically you string all these rules together and they live in a table. And then to give high level logic, such as if then else, we sort of string these tables together and we let a packet sort of jump through. So that's what this sort of pictorial representation at the bottom of the slide is. So it's a packet-based processing pipeline. So you get a packet in the left and it starts in table 0. And then you can have branches. So you can have rules that tell it to go to different tables. And eventually the packet hopefully comes out at the end, or maybe you drop it because you don't want it on your network. All right, a little bit of history of the project. So it started with a sort of rough set of lofty goals that we wanted to achieve. So we wanted to, we set out to write good software. You know, no one really sets out to write bad software, but we kind of wanted to make sure that it stood up to being run in production. So, you know, it wasn't just going to crash every other day. We wanted to sort of foster this ecosystem of reliable hardware. So at the time, the number of SDN switches were few and far between, and the ones that did exist were quite buggy. So we kind of wanted to grow the community of SDN switches. We wanted to put it in production and run it. That was a very clear goal from the get-go, and that comes back to, you know, knowing it's robust and knowing there's reliable hardware. You know, we need to actually test it and deploy it. And production testing is where you, of course, find all your edge cases. And for networking, unfortunately, there are lots of edge cases. We wanted operators to be comfortable using it. We didn't want it to seem foreign or strange or be complicated to work with. And we wanted to interop with existing tools. We didn't want to write the Faucet network monitoring system or the Faucet you know, debugging tool set or all these different things. We wanted ping and trace route to work. We wanted you know, all your standard network monitoring systems to plug in and work and that kind of thing. And so back in 2014, 2015, we had a pretty good, pretty nice supportive SDN community in New Zealand. And we all kind of were working on our different projects, but we all kind of settled on, like, Faucet was the thing we kind of wanted to take forward. And so Rian's, which is our NRAN, they got involved in starting out with the project. Josh Bailey, who was working at Google at the time, he was in New Zealand and joined the project. My university were there. There are other universities such as Victoria University got involved. And today we've sort of taken that New Zealand-based project, and now we've got 53 contributors from all around the world. And about any given week, we have about 6 different people working on the project in various different forms. And we just recently turned 6 years old. So why Faucet? So this is going to hammer the point a little bit again, but yeah, it's small, it's simple. We've got 10,000 lines of code, and for every line of code, there's two lines of tests. So there's 20,000 lines of tests. And anyone who's written software before knows the tests are, you know, where the project really succeeds, when you actually start to test what you're doing and know if it's right or not. A lot of other controllers don't use a multi-table pipeline. They just use table 0, and they don't have this branching logic. And the branching logic in OpenFlow is when you start to get really efficient rule sets, because instead of having to match all types of packets and all different pairwise unicast flows on your network, you can separate that out, and you can get a lot smaller numbers of rules, which fits better in an ASIC in Silicon. We're also multi-vendor without any drivers. So we just use standard OpenFlow, and we don't program different vendors in different ways. And this is key to making sure we get this dream of multi-vendorism. So, all vendor switches and Faucet behave the same way. You get the same features and they work the same way, which is quite cool. So very well tested. The way we do high availability is quite different to other SDN controllers. So we didn't want to have this tightly coupled cluster where we have to manage state between all the members in the cluster. So what we've done instead is use the power of idempotency to do HA. So when you deploy multiple Faucet controllers on your network, because obviously you want some kind of resiliency there, you kind of just give them all the same config file, and that's their state. And then everything else is ephemeral state. Everything else they calculate as they run. And all you do is point your switches at multiple Faucet controllers, and because they've all got the same config and they all go through the same algorithms in an idempotent way, you get the same rules on the switch. So that's how we're kind of doing HA. And the other very key thing is the controller is not in the forwarding path. So what I mean by that is when you've got a packet going through your network, it doesn't touch Faucet. We'll occasionally copy off a couple of packets to do learning, but we try to do that as very minimally as we can, because that's when you lose an SDN, when you have to copy to the controller. Because the controller to switch path is the slow path, and it can get easily overwhelmed. So that's how we get sort of these high multi-terabit per second speeds, because we don't have to process every packet. And kind of the core Faucet design is around these kind of useful primitives that you'd expect to see in a networking controller or even a switch or a router. So we've got forwarding in there, we've got VLANs, policy and ACLs, which we'll get into a bit later. We have a fib in there for V4 and V6, and you can kind of chain these together and kind of build whatever network you want out of these features. We have a couple of different protocols for interop. We always wanted Faucet to be a thing that you could just plug into a regular traditional network and it would just start working. So we've got ARP in there, IPv6 neighborhood discovery. That's so that you hosts on the network can use Faucet as a router, so they can look up the MAC address for Faucet. We have BGP for route exchange, LACP for doing redundant link bundles, and stacking's our kind of idea of, it's not quite like a vendor stack, but it's our way of plugging multiple Faucet switches into each other, telling Faucet that these are all plugged into a certain topology. They're all sort of one entity. And Faucet runs a number of different path selection algorithms to automatically deduplicate loops on the network. So we call that one a spanningless spanning tree. So we have a version of spanning tree that instantly converges and runs once, because obviously with the central view of the network, we know all the switches, we know all the paths. And so we can run that very quickly, which is quite nice. Another key thing we do is if you're not using a feature, the code's not running. So that's less chance of things going wrong. All right, so how do you configure a Faucet? What does my network look like now? So we've gone with YAML, which if anyone's doing your cyber infrastructure-y things, you've probably seen YAML quite a bit. Might even be quite sick of it at this point, but one thing I'll say about YAML is it's quite nice to read. So that's got one benefit over other formats. So here's a very simple Faucet config on the right here. And we've just basically simply got single VLAN. It's called Office, VLAN ID 100. You can put some descriptive fields in there so that when you look in your monitoring dashboard, you know what that means. And then Faucet has this notion of a virtual IP or a VIP. That's the IP it joins the network on, so that you can do ARP and V6 neighborhood discovery to it. You can use that as a router, that kind of thing. And then we've basically just got one switch here. It's got data path identifier 1. In this case, it's a software switch, and it's just got 2 ports on the same VLAN. So it's very simple. And then here's kind of what a high-level architecture overview of the system looks. So down the bottom, you have a set of SDN switches. Faucet's a 2-controller system. So you'll see on the screen, you've got Faucet and Gauge. And the reason, again, we did the 2 controllers, and we wanted to limit the number of things that could go wrong. So Faucet is our read-write controller. It consumes that config file. It makes all the OpenFlow rules and pushes them down to the switch. Gauge is a read-only monitoring controller. And so it just sits there and it pegs away at polling the switch for port stats and packet drops and all these different things and stores in a database. And the reason we did it this way is Gauge could have the worst bug in the world. It could just crash for whatever reason. It typically doesn't, but the theory is it could. And your network keeps working because Faucet only has a small amount of actual live code that's making the network work. We've got a number of different APIs at the top. So you can BGP peer to Faucet. You can receive or subscribe to events from Faucet if you want an external system to be part of the decision-making loop. And then we've kind of settled on Prometheus, which is quite a nice time series database and sort of query engine for metrics. You can plug into different ones to Faucet, but Prometheus we found to work the best. And then once you've got a database of all the metrics, you can sort of plug in a Grafana or some kind of other dashboard to sort of see what the network's doing. Another interesting thing is Faucet sends instrumentation to the database. So you can see as it goes runs its loops, as it's working on things, it tells you how much time it's spending doing things. So it becomes quite nice when you're trying to work out if you're hitting the limits of something on your system. And then what a basic Faucet pipeline looks like. So this is a Faucet pipeline if you were to turn on most of the features. If you don't, if you just have a simple feature set on, Faucet will only put in the tables or the rules that it needs to process the features you've turned on, and that's once again to be lightweight on the switch hardware. We don't want to use up more TCAM or hardware resource than we want to. But if you were to turn on all the features, you get a packet processing pipeline that looks like this. So just starting at the top, so we start with a port ACL table. We can apply policy to an individual port. And then we jump into table 1, VLAN table, where we make sure all packets have a VLAN tag on it. So we can make sure as they process through the rest of the pipeline, we ensure VLAN separation. Then you can apply policy to an entire VLAN with a VLAN ACL table. And then you jump into an ether source table where we start doing MAC learning. At that stage, we would determine if we were doing a routed packet or a forwarded packet. If it's being routed, it would go into a fib and would work out where to send what the next hop for the packet is. The VIP table is where we handle packets that were destined for Faucet. And then we'll eventually end up in the FDS table where we're looking for the output port for the packet. And if we can't find it, we'd ultimately flood the packet. So a little bit more on policy. So yeah, as I said, policy is a way of changing the Faucet behavior without changing code. An ACL is basically just an OpenFlow rule. It can match on anything OpenFlow can in terms of the packet fields, packet header fields. And an action might be drop, it might be allow, it might be output. So you can copy the packet if you want to do some debugging and look at what the packets on your network are. You can even modify packets, so you can modify the MAC address, you can modify IP addresses, whatever you want. And so as we're going through that pipeline, you would have seen we've got a couple of different types of ACLs. So these are sort of different for you for other things. So in your port-based ACLs, you might do your traditional sort of L2 filtering. So enforce who can do DHCP and DHCP6. That's where you can put your router advertisement guard. So the NFV offload example I've got there is sometimes you want an external system, some kind of server to handle a particular type of packet. So maybe 802.1x EO poll packets you could carve off and send to a NAC somewhere. And so you can use an ACL for that. VLAN ACLs are when you want to apply consistent policy to a group of things. So if you do it individually per port, you've got 100 ports on your switch. That's 100 in ACL rules, which is kind of annoying. Or you can apply it once to an entire VLAN, and then it's just installed on the switch once. And so one funky thing I do on my work SDN network is I have a V6 only SSID. And I know it's V6 only because there's a Faucet ACL on that VLAN that backs that SSID that drops anything apart from IPv6 packets. So you literally, if you were to send a V4 packet onto the network, it will be dropped at the access point layer, which is quite cool. And then one thing I haven't really got into yet, Faucet does inter-VLAN routing. So you can have a mesh of VLANs that you want to talk to each other. And you can also apply policy for limiting sort of how that works. And so what does a policy look like? Well, surprise, it's just some YAML again. This is what a V6 router advertisement guard policy would look like. So you just kind of match on the packet type. In this case, we're doing IPv6 packets, ICMP v6, network proto, and we're just looking for router advertisement type, and you just say drop, and this Faucet in the switch will handle the rest. So I've said a lot, about how key testing is for us, and just to put some numbers around that. So we have both unit tests and integration tests for the project, and we're over 90% unit test coverage. I think somewhere in the order of 92% of lines of code go through a unit test. We have an integration test that basically spins up a virtual network made out of virtual switches and runs a number of different network scenarios with different Faucet configurations, different numbers of hosts doing different kinds of traffic. And we inject real packets into that virtual network and test that the packet goes the right place, or it doesn't go the right place, it gets dropped. And we run both against every single code change to Faucet. So that's how we're avoiding regressions on the project. That's how we know when we commit new code that we haven't broken something that used to work. As long as there's a test case for it, that test case will automatically test that that functionality keeps working. And this has been really key to us to allow us to refactor regularly. So we like to, in Faucet, we like to write something, our software development approach is the first cut of a feature, we'll just write what we think we want. We'll throw it into the repo, we'll give it to a user, and we'll go, hey, is this how you wanted the feature to work? And they'll be like, actually, you've kind of got this wrong, or maybe it doesn't scale to thousands of hosts like we want it to. And then we can refactor over and over again that feature. And because we put tests in there, we can know that the feature keeps working the same way, which is quite nice. Another really cool thing you can do with integration test suite, and going back to that, we want to foster this ecosystem of reliable hardware. We give the integration test suite to the vendors, of which we have about 7 vendors, I think, that support Faucet right now. And they run that test suite against their switches, and they tell us which tests pass, which tests don't. We work with them to get the failing tests to pass. And this is, in a way, automating qualifying devices for Faucet. So when you buy a switch that has the Faucet seal approval on it, you know someone's already run through all the features on it and told you it kind of works. And they also use this to QA new firmwares that they put out. They use it to test new products. So often we'll put a switch on a Faucet network, and you'll see this in a second when I start talking about our actual deployments, that we've never seen before, but we trust it's going to work on the network because someone's run this test suite and told us it passes. So another kind of thing that this whole SDN paradigm allows you is this much more novel way of running a network, this kind of idea of push on green or automation. So you can leverage this integration test suite as a network operator to deploy your network. So if you've got sort of test cases in the integration test suite that, maybe my network relies on a particular ACL, or it relies on a particular kind of VLAN forwarding behavior or something. As long as there's a test suite that covers that, you can write your Faucet config, your Faucet.yaml, you can check it into some Git system. It can run a CI test suite over your your new config you just pushed. And if that test suite passes, you can go on to automatically rolling out that config to your network. You could do a canary staged rollout where you roll out to a certain small part of the network, and then if that works as well, you don't get alarms from your network monitoring system. You keep rolling it out. That's kind of what this idea of push on green is. It's removing the manual steps of making sure network rollouts work, which is quite cool. So one example of this, every week on my network at work, my Faucet network at work, we do an automated deploy of new Faucet code. So, and I couldn't do that as a human. That would just take up way too much of my time. So there's this nice system you can have around automatic deploys, which is quite cool. So if you've liked what I've said so far and haven't disconnected from the call, maybe you want to think about deploying SDN. So my key tips that I've learned over my sort of 4 or 5 years of deploying Faucet networks. So it's always best to start small. You want to kind of build an island on your network of SDN, not this wide interconnected city. And the reason I say that is that there's a lot of stuff for your teams to learn. There's a lot of new things and new ways of thinking that you need to learn. And having a small part of the network that you rely on somewhat, but if it went down, your whole organization's not making money anymore, that's quite a nice place to start. And the reason Faucet lets you do this is we've got all those traditional protocols in there for plugging into a regular network. So pretty much all of our Faucet SDN networks to date have been plugged in at some point to a traditional network that has provided connectivity to other parts. And that was a very key thing we wanted to do with Faucet from early on. Other controllers had this sort of idea of, everything would have to be an SDN greenfield deployment. Everything's brand new, doesn't work with anything that we had before. But Faucet's kind of like a stepping stone that lets you have half and half traditional, half SDN. And then once you've got a little deployment, you want to test it, you want to understand it, you want to start with a simple config and then go, oh, what if I added this? What does that do? Oh, and then I can add this on top of that. What does that do? And sort of grow your sort of understanding of what's going on so that when things do go wrong, because, it's networking, things are always going to go wrong, you'll be confident in being able to fix what comes up. And then basically you just have an iteration step where once you're comfortable with what you've built, you build something bigger, you add more functionality. And that's what I've found the best way to deploying this stuff is. All right, so what sort of deployments have I done to date? So the notable ones are sort of these three. So the very, very first deployment of Faucet I did was, we tried to find a venue where we were like, okay, it's the early days of Faucet, still the early days of SDN. Where could we deploy SDN to know if this crazy idea will ever even work? And so we picked a network operators conference. We picked the New Zealand Network Operators Group. They have a yearly conference, and we said, if we can provide a network to them and they only complain a little, the network operators, they're going to complain about something. But if they only complain a little bit and the network mostly holds up, we should be able to get this deployed in other places. And so Internog 2017, we deployed a couple of switches, Faucet, and we ran the whole conference on it. Only had sort of one minor outage before the conference began, but during production time for the conference, everything was fine, minimal complaints, and the conference even invited us back the next couple of years to redo the deployment. So obviously they weren't too scared off about it, which was really cool. And then kind of what I did is I took the NZ knowledge that I'd learned, and I deployed a Faucet network at my workplace. So we're the one network group based at the University of Waikato. We need research networks, basically. So our research network at work is all Faucet and has been for about probably 3-4 years, something like that now. It's not many MAC addresses, but we've got a lot of number of switches, 3 or 4 different vendors. There's a complicated controller layout. So that's kind of what I maintain day to day. And then the big one's this SINET 2018 deployment, which I'll talk to you about today. I was kind of hoping that I could give a more recent deployment we've done of Faucet. We were meant to do quite a large one at Interop Tokyo last month, but due to various ongoing problems with the world right now, we weren't able to pull that deployment off, considering the conference was cancelled. But SciNet is a really good talk as well. So I think you'll still enjoy what I'm about to talk to you about. There is actually one more deployment I could have talked about. I've just in the last couple of weeks done a deployment of Faucet at my house. So this call right now I'm giving to you is I've got a 5 terabit per second Faucet network at my house right now. And hopefully if I don't drop out, that deployment's working as well. But the SciNet one's more interesting than my house. So normally when I give this talk, I have to give a bunch of context about what SC is. For this group, probably not, but I see there's a few people on the call that aren't from the science community in the US, so I'll go over the context. So basically every year there's this huge, massive HPC conference. It's been going forever. The 30th anniversary was November 2018 when we did the deployment. And as part of the conference, they do this big SciNet network, which is a really cool network. It provides all the internet for the booths, for the conference rooms, and it's basically one of the world's fastest temporary networks. It exists for a couple of weeks, and the amount of work and resources that go into it is just something incredible. And we were lucky enough to do a Faucet deployment as part of SC18. Okay, so just to put some numbers around things, here's my favorite, I call him the Chief Diagram Officer, Lance, and his proud network diagram. So each of those boxes were different network elements on the network we built. And, going on the line with it, it's like the world's largest temporary network. So for SciNet 2018, we brought in 4.02 terabits per second of internet connectivity. The on-network connectivity was way more than that, but that's how much internet we had. There's like $52 million worth of loaned hardware, over 4 tons of gear we had to set up. There's 225 people running this thing. It's a huge thing. Like, that's what I want to get across, how big this thing is. And so how did small little SDN controller in New Zealand get involved with the project? Well, once again, we were looking for a challenge. We don't like getting bored at Faucet, so we kind of emailed some people we knew that were involved in SciNet, and we're like, hey, do you want to do like this SDN thing on your network? Do you want to give our controller a go? And the great thing about SciNet is they're very encouraging to new experimental ways of running the network, and they always have, which is really cool. It's really great for people like us to be able to get these deployments where we can actually test in production and see, have we got something wrong? Are there some learnings we need to have? It's really nice to have these deployment opportunities that people let us, trust us with their network packets, basically. And so it was an interesting project. I'm based in New Zealand, so is Josh, who was working on the project. And then we had a number of different people working on the Faucet SciNet team in the US. And we just basically did months and months of video conferences trying to work out what we could build that would be beneficial to SciNet. We even had to talk to a couple of people in Europe, and all of those people that do video conferences to lots of strange places will know, doing conferences multi-way between all regions in the world is quite difficult. Some people had to draw short straws on who had to wake up at 1 a.m. But anyway, we got through it. And the very key thing that we started was setting a scope. We didn't want to get your scope creep of committing to more than we could actually do, or just letting the project run wild. So a couple of key sort of requirements we put on. So we decided basically that we'd run it in parallel with the regular network, just in case there was some strange bug we hit or some strange problem. We weren't, going to let the network down, but we could cut across to the regular network if we needed to. And then basically Faucet just had to pair with the core routers at SciNet, and we'd do some route exchange. And then we were going to provide a percentage of the booths on the show floor with some internet access. So we ended up doing about 25% of the network was on Faucet, and at no point did we have to cut anyone away from Faucet. It worked quite well, which is nice. And basically a booth in terms of the network is just a VLAN and a subnet. So we just had to allocate a bunch of VLANs and some IPs. And then we need to provide some connectivity. So a booth could buy a 1 gigabit, a 10 gigabit, or a 100 gigabit connection to their booth. So that's right, in your little trade stall in the middle of a big conference, you could have a 100 gigabit internet connection if you wanted. And quite a few people picked that option, which is quite cool. So we knew we needed scale to get this network off the ground. And then to sort of track all of the VLAN and subnet information, there's this customer information database, which comes from a Django web app. So we just needed to interface with that to pull out all the information so that we could generate the right faucet config. And we did some initial sort of diagramming and design work. So the way Signet works, for those who haven't run into it before, they kind of this NOC layer and DNOC layer. So the NOC is kind of, it's the network operations center in the sense of that's where the 225 network operators sit. But there's also this big core of the network that sits in the NOC, and that's how it gets the term. And then you have all these fiber breakouts that go to the DNOC, the distributed NOC. So some people might call that core and access, but for the purpose of this talk, we'll call them NOC and DNOC. So we need some devices, and we need to put them in places and draw some squiggly lines to connect everything up. And kind of, we did this backwards. So we pitched the project, we did the design work, and then we went and picked the vendors. But we can do this because it's Faucet and SDN, and we have the integration test suite. And so we know there's the set of switches that work. So the only thing we're concerned about at this point is, would people help us with our crazy idea? Because we needed some switches. So we called up LA Telesys, Cisco, NoviFlow, pitched the idea and said, hey, can you send us some free switches for 6 months so we can test and then do some design work and then throw them on this network? And surprising them, all of them said, yes, here, have 2 switches. I saw some of the dollar amounts that they sort of loaned to us, and they were very friendly. I'm very appreciative of them helping the project. And basically, just to hedge our bets a little bit more, we wanted to build a network and deploy it in a test lab and make sure it all worked. We're very prudent and careful people at Faucet, so we wanted to see it actually working before we committed to deploying it in the conference. So we shipped everything out to a lab, an AirSnet lab in Berkeley, California. And now, unfortunately, ordering a bunch of switches for free and getting them shipped to one place in the world, it's not instant like I had hoped. So while FedEx was delivering some boxes, we could do some work. So we iterated on that design. So now that we had some vendors and we had some model numbers, and we knew what the port densities were going to be, we sort of started to draw some diagrams. So this is basically what we ended up with. So on this diagram, you see at the top is the 2 NOC routers supplied by Signet. So that's the 2 Signet core routers. And then we did 200 gigabit lags up to those. We BGP paired with them into our core switch. So we had a BareFoot Tofino 100 gig 32 port switch in the middle. And then we went through a bunch of data center interconnects. So they're just fiber interconnects. And then into our DNOC switches, which is where people would plug their booths into. So we had a wide variety of different switches from different vendors, and we had about 9 terabits per second of capacity if we needed it. And we also sort of allocated where our functionality on the network was going to happen. So Faucet was going to do all the VLAN separation. It was going to provide all the IPv6 router advertisements for everyone in the network. It was going to do all the inter-VLAN routing and provide a bunch of network security policy. We decided to NFV a bunch of services that Faucet didn't have good support for at the time. So we had a 10 gig interconnect between the core switch and basically a server. And we ran ISC DHCP server for allocating all the V4 addresses. And we ran Bird for all our BGP. And then we were just using those ACLs as we saw before to sort of steal packets and send them to the NFV controller. And basically, we followed the model that I was talking about before. We wrote all of the scenarios we came up with as test suites. We added them to the integration test suite. And then that meant as we were changing code, as other people were working on Faucet, they weren't breaking what functionality we're going to need to rely on for the conference. Because for the conference, we deployed the release that had just come out like the week before the conference. We weren't running a special build of Faucet, we were running real mainline Faucet, which is cool. And we also built a scale model back in New Zealand out of completely different vendors and at 1 gig. But because the kind of SDN model and the Faucet model of all these tests and everything, we figured as long as we can get it working at 1 gig, it should also work at 100 gig as well. And I also started working on some automation. So, you know, probably don't need to tell this group, but automation is the idea of defining a set of tasks once, and then you can repeat that set of tasks over and over again with no cost. And this is really great for network service definitions, where we've got lots of different customers all using the same sort of core set of services. And for Faucet SciNet deployment, we heavily used Ansible for sort of doing all the config. And so what we ended up with was this kind of model of, you know, there's a source of truth of the network that's coming from the Django web app that they provided. And then we basically had a little Python script that could walk all the Django database models. And it just dumped all the custom information into a YAML file, because I don't know, I kind of like YAML if you haven't worked it out yet. And then we basically use YAML as an input into Ansible, and you just ran the Ansible. It had a bunch of different roles for configuring the DHCP server, for configuring Faucet, for configuring the router. So all of our BGP config was Ansible generated. And so at the end, you just end up with a text config file, and Ansible would roll it out and apply it for us. And so we kind of ended up with, you can see down the bottom, so there's 290 lines of input, of customer input. And then we wrote a very, very small amount of Ansible, you know, 180 lines of actual core Ansible. There's 260 lines of templating. And we got out over 1,000 lines at the end. And, you know, we ran this a couple of times during the conference, and it was a lot faster than writing 1,200 lines by hand every time, I'll tell you that much. And so I published all this. So you can look at the Ansible, you can look at the generated Faucet configs for the network, and that's all open. And if you want to see what a big network looks like, those are available. But hey, FedEx did their thing. We got all our boxes, and we started working on testing. So we already basically had most of the Ansible ready at this point. So I just kicked off an Ansible deploy on the network after Nick Braulio gallantly flew out and plugged everything in for me. And then the idea was throw a lot of traffic at it and see what sticks. I found network namespaces in Linux are great for this. So I had a little Linux box in the test lab in Berkeley, and I basically just spin up thousands of network namespaces, and each namespace was a fake booth. And I wrote a whole bunch of horrible, terrible bash scripts to manage my zombie cluster of network namespaces. And so with things like onAll, which could log into every single namespace at the same time and run a command. And so you could just have a ping all command, and that would test connectivity, make sure everything that could ping. And then we could test throughput as well. There's a random iPerf script. It found a random pair of hosts on the network, and it spun up an iPerf server on one, iPerf client on one, and verified they could talk. Now at this point, we're only testing at 10 gig. So I never saw the network run at 100 gig until the actual conference. But we figured, you know, 10 gig, 100 gig, what's the difference? It's only a 0. And so once we'd successfully completed all our testing and we were happy, we shipped it off to the conference venue so that it could eventually get set up. And the way SciNet works is they stage the network before deploying it properly. So as I said, there's so Faucet was just one project on the network. There's tens or 20 different sort of projects that are happening on the network. And so SciNet staging is the first time the whole network's plugged in together. So the routing team, you know, plugging into the you know, data center interconnect team, plugging into, you know, the Faucet team, all for the first time. So it's a little bit of a stressful time. You know, inevitably there are going to be bugs and that kind of thing. So this is kind of like the interrupt testing side of the event. This was the Faucet team who turned up for staging to plug it all in with the absolute chaos of cables behind them. And we were pleased to be one of the first teams up and running. and our network booted first time with no issues. So in this photo, we've got Josh Bailey, got a couple of people from the vendors making sure everything's working, which is great. And then once sort of staging's all done, we have to basically move that network and deploy it to the conference proper. So this is what the this is about half the warehouse space layout for the conference, and this is before it's all sort of begun. And we literally do a forklift load for SciNet. So this is another very stressful part of the project when $50 million goes up on a forklift. But luckily, they've got some really good forklift drivers there who are very professional and not even a single scratch or dent or anything, which is quite impressive. And then basically, staging's done. We've sort of used a forklift to track the network to the right place. At some point, the customer database is basically finalized, and we basically hit enter on a laptop, and Ansible rolled out our network. And then we had to basically make sure all the booths, as they got installed, could connect to our network. So here's what a DNOC looks like. It's just a little cage out on the show floor area. And on the left there, on the right there, sorry, you'll see there was the regular SciNet switch. And then below it in every DNOC would be a Faucet switch. And then a big honking great load of optical transport gear. And so this is the NOC area. So this is where our 32 port 100 gig NoviFlow switch was. And that's the sort of core of the network. And now, yeah, I said we have never seen the network run at 100 gig. So we kind of wanted to see if that worked or not. So luckily, we were in the right place to find people with 100 gig. We literally just walked out after we'd built the network and sort of started talking to booths and very quickly found someone who had these portable handheld 100 gig load testing computers. And we're like, oh, that's fantastic. Can we borrow it for half a day to see if the network works? And so we just basically put 2 of these on opposite sides of the show floor, plugged them into the Faucet network and ran some iPerfs. We actually managed to crash iPerf, which I've never done before, but that's why there's gaps in this graph. But yeah, we saw our first 100 gig spike, which was very exciting to see. Let us know that what we built was working fine. And then basically for us, that was most of the stress over. Building the network, deploying it, letting it run wasn't too bad. You basically just get a bunch of tickets assigned to you. Pretty much all the tickets were, we'd have to go roll some fibers or swap some optics. A lot of people tried to plug multi-mode optics in at their end and connect to our single mode optics. Anyway, it was all your kind of traditional sort of networking issues. And the fixes were pretty simple. Didn't have to write a single line of code, which was nice. And then basically, after all this work, so yeah, we spent about 7 months planning this thing. We spent about 3 weeks to a month testing it in the lab. We spent 3 weeks in Dallas in the US doing all the setup. It all comes crumbling down in 1 day, which is quite impressive and chaotic to watch at the same time. And this is most of the Faucet SciNet crew from all over the place. And yeah, we're very, very happy with our deployment. So what did we learn throughout this whole process? What were kind of the learnings? So we definitely found that that the automation was really helpful. So us taking on all the sort of common connections. So we didn't take on any special SciNet booths. So at SciNet, people like a lot of custom things. So there are booths that get multiple wavelengths that go to like Europe and all these strange things. But we didn't take any of that on. We just wanted to take on things we could easily automate. And SciNet definitely found that this helped freed up time to spend on these more sort of custom customers, and with us just taking on the bulk customers, common customers. Another great thing, Faucet allowed us to effectively ignore all the underlying network equipment. It wasn't until basically a week before SciNet that we had confirmed what all the switches were. Because at the last second, one of the vendors swapped the models for switches on us, but they told us it passed the test suite and we plugged it into the network and it worked fine. So that was really quite exciting to see in practice, something that would sort of been saying for a while, but we actually got to test that. And we got to prove that, 10,000 lines of Python can easily handle many terabits per second, and I suspect it will continue to do so. And if anything in this talk has piqued your interest, so we've got a very nice tutorial series on our website that you can configure Faucet in a virtual environment, play with all the features we've talked about today. You can even grab the Sinet config off GitHub, and you can set it up all virtually and pretend you're running a very large HPC network. So we'll leave that link on the slide. And we're always here to talk to you. We've got an RSC channel, we've got a mailing list, we're on Twitter. I'm, getting bored just sitting at home, so please get in contact with me, reach out. So I'll leave my email address on the slide as well. And I think there's some time for questions, if I'm correct, if anyone has any.
Yeah, we have time for questions. Thank you again, Brad. Really interesting stuff. So if anybody does have questions, please type them in the chat room and I'll repeat them back here. Looks like we got our first one from Jim. I assume that an OpenFlow agent is running on each switch. Did you get those from the manufacturers?
Yeah, yes, all of our OpenFlow agents are from the switch manufacturers. The only special case, I guess, is NoviFlow, who are their operating system will run on different white box hardware, but every other vendor that Faucet supports, it's a traditional network vendor, and they provide the OpenFlow agent.
Okay, thank you. And I have a couple that I jotted down here just to sort of seed the questions. If anybody else has others, please enter them in. So I guess more of a practical question. At this point, what's sort of the library, the breadth, the scope of manufacturers that have passed your testing? What sort of switches out there can run this sort of out of the box?
All right, let me test my memory here. So Allied Telesys, most of their switches support Faucet. Cisco Catalyst 9K support Faucet. NoviFlow, all of their switches support it. HPE Aruba, if you're using their, let me see if I can remember the models. There's a 2930 and there's a big chassis switch. I can't remember the model off the top of my head to support it. The newest vendor we're talking with at the moment, which we hope to announce soon, is Arista. So my home 5 terabit per second network is using Arista. They'll be the newest ones. There's a bunch of different software switches, so OpenFlow, OpenVSwitch, sorry. Let me just check my list, make sure I didn't leave anyone out. That's mostly it. And then we're always looking to engage with new vendors as well.
Okay. So it sounds like a pretty good number. I guess a related question is of vendors who sort of get involved and want to start testing with you guys, are there any sort of common errors or things that they need to do to sort of get their hardware ready as they're going through the test suite? Any sort of common things that you guys see, or is it sort of all over the board in terms of their support and they're ready to go with it?
Oh no, I'll always say this: networking is death by 1,000 paper cuts. The edge cases are terrible, and everyone always gets the edge cases wrong. And that's not just implementing OpenFlow support. That's I'm sure all of you have played with brand new switch hardware, and the vendor's just launched a new, completely written from scratch network operating system. It's the same bugs over and over again with R, with spanning tree, with OpenFlow. And that's just because there's so many different weird edge cases. So one thing we've done with Faucet is in that test suite, every time we see a weird vendor bug, we put it in the integration test suite so that the next vendor that comes along finds that test and goes, oh, okay, we also got that wrong. And I wonder if some of that comes down to some of the programming APIs they get from their ASICs. So a lot of the vendors are using, obviously Broadcom ASICs, and Broadcom makes a bunch of things really hard. So one of the common complaints we get from people with Broadcom is incrementing decrement TTL for routed packets is really difficult because of the API in there. So I wonder if that's an artifact of how they're sort of building their switches and their kind of internals.
Okay. And I got one more. So at one point you had said, the best way to get started is to start small. We have a lot of different people on this call today who represent networks of different sizes, campus networks, laboratory networks, regional networks. For somebody who is interested in trying to experiment with this, and I'm sure you have tutorials and things on the website for the brass tacks of it, but what's sort of the most recommended approach on getting started? Starting with a single device and a single use case, user-facing versus engineer-facing. Any sort of recommendations on somebody who would want to test this out?
Yeah, so I think I got two answers here. There's obviously there's the prudent approach of put yourself behind it. You as a network operator or engineer, put yourself behind it. That means you can only break yourself. If you break it, where to go to complain. You go to yourself. If I find what's useful for me is, if I build a little lab network off to the side that no one's behind and it breaks, I just leave it because there's always more important work to do. There's always more important things to spend time on, and so it's an easy way for a lab to atrophy when it breaks one day and you never bother to go back looking at it again. So having at least a couple of people that rely upon it does put that sort of operational pressure on to fixing it when things go wrong. It also forces you to put monitoring on it. A lot of lab networks just sort of sit there and, you don't put monitoring on it because you don't want alarms and that kind of thing. But having some amount of operational pressure, I think, is good, and forcing you to prioritize it over the other million fires you have in a given day. But obviously not put the entire company behind it or put everyone behind it. And I promise, once you get things working, it is pretty reliable. So one kind of anecdote I could say. So I work for a university. We're quite a small university here in New Zealand. We've been invested on our corporate network at the university for some time. And for the past couple of years, because we run a very massive flat layer 2 network at work at a university, we've had a number of spanning tree outages, and I've got a number of colleagues that work in different parts of the university, different buildings, and when our corporate regular university network goes down, they all come up to our offices and use our Faucet network to do their important video calls or send some emails or something. So it can be more reliable than a traditional network, which is we've found quite hilarious at our workplace. But I'm sure all of you have beautiful networks that don't go down. So I applaud you on that. It's just us not spending money.
All right, there is two more questions, but I wanted to point out that even at ESNet, we have some small deployments in our office network environments, one in the Champaign network that Nick Braulio manages, and even the ESNet director, Indramonga, has stuff behind his. So we're using this on a variety of things. Mohammed asks, when should you not use Faucet, assuming all the hardware vendors are supported? Are there any use cases where there's a particularly bad thing to sort of implement?
Yeah, great question. So yeah, Faucet at its heart is an enterprise SDN controller. So there are a lot of things that don't look like enterprise networks, and yeah, you shouldn't use it there because we haven't really tested it there. So that would be your more sort of WAN backbone type networks. It's not smart enough to do very advanced traffic engineering or route steering. It's also built around SLAs and SLOs for an enterprise network. So we always target time to remediation for Faucet when something goes wrong should be faster than someone running up to a building and replacing an optic or a switch or a failed power supply. So we're not doing sub 50 millisecond telco style fault tolerance. So that is definitely a very poor place to put Faucet. But anywhere where these kind of engineering tolerances allow for you know, second or sub-second outages, I think that's a good place for Faucet. Also, if you just want to simply blindly copy over an enterprise network config from a Cisco and a Juniper and put it on Faucet, that's another bad use case. Faucet doesn't support every protocol that a switch supports for, because we just didn't want all of the protocols. So there's definitely places where Faucet isn't the right fit.
All right, and last question from AJ. Can you throw some light on the tools that were used for automated testing and CI/CD?
All right, so we've gone through almost all of them. So we're an open source project at heart. So we're not paying for huge data centers of test infrastructure. So what we use mostly at the moment is Travis CI, because they have sort of an open source free plan. So Travis has a little bit of problems. So and they only let us run 5 concurrent jobs, which sort of slows down development a bit. So we're looking at moving to GitHub Actions, which on their free plan we can do 20 concurrent tests. And then what the CI looks like. So for the unit tests, it's just PyTest, which is a Python unit test framework. And for the integration test suite, integration tests are always the worst to write. They're horrific because you have to deal with real hosts running you know, code that's not yours. So what it is at the moment, and we've got it working pretty well, is it's a series of Docker containers that run with Mininet inside of it, and then Mininet orchestrates the spinning up of Linux containers stacked as hosts, and OpenVSwitch switches to run as virtual switches on the network. And we have the developer of Mininet, Bob Lance, working for us, and he's tweaked our test suite to work well with Mininet, and tweaked Mininet to work well with Faucet, which is quite nice. And then we have sort of one other test suite. So every night, New Zealand time, the fine folks in Siberia and Alberta, Canada, that they loan us a bunch of VMs on their OpenStack cluster. And we run what we call the fake hardware tests. So we spin up a fake switch, a virtual switch, and we run the test suites as if it was a vendor running the test suite in their office. And it's just to catch out any problems with the test suite being run for a vendor. And so that emails us if there's any problems. So it's yeah, a lot of different kind of platforms and that kind of thing. And mostly we've written everything from scratch, and you know, there's some negatives to that approach and some positives.
All right, well, that was all the questions. Thanks everybody for participating this week, and thank you, Brad. If you can send me a copy of the slides, I'll make sure that those get posted.
Great.
And we were going to be on a 2-week pause for the people who are still listening. We'll be off on the 22nd and the 29th, so we will return on June 5th. So hope everybody has a good holiday weekend, and everybody's staying safe and healthy. We'll talk to everybody soon.